Most people step over the very stones that signaled early gold rushes. The assumption is simple but wrong. If it doesn't shine yellow, it isn't gold. But in the field, some of the richest gold-bearing rocks show no yellow at all. Just streaks of rusty red, dull gray, or even bluish-black surfaces that don't stand out unless you know what to look for. The surprise lies in how gold travels. Instead of existing as nuggets on the surface, most gold originates deep underground, forced upward by hydrothermal fluids that deposit it within veins, cracks, and porous zones in hard rock. As those fluids cool and pressure drops, gold settles, often alongside quartz iron oxides and sulfide minerals, locking it inside formations that look anything but valuable. In practice, this means a lichen-covered chunk of quartz shot through with reddish stains may carry more worth than a gleaming piece of pyrite or a sparkling river pebble. One of the first missed signals is iron staining. Where groundwater weathers sulfide minerals like pyrite or arsenopyrite, it leaves behind rusty red or yellow streaks, often on quartz or schist. While most people dismiss such staining as weathered junk, experienced prospectors stop and check. These discolorations can mean gold is, or was, present in the system, even if invisible to the eye. Even more overlooked are rocks embedded with tiny specks of metallic gray or brassy grains. These may be microscopic inclusions of gold or gold-bearing sulfides like chalcopyrite. Many assume such rocks are worthless until a crush-and-pan test or lab assay proves otherwise. Often, gold appears only after physical processing, crushing, roasting, or acid treatment, to release it from its mineral bonds. This means that recognizing a gold stone starts not with shine but with context. Where the rock lies, what it's attached to, and whether the surrounding terrain supports hydrothermal or metamorphic history. In some cases, a single gray rock with iron crusts found near a fault line or quartz vein can become the starting point of a profitable discovery, if it's tested rather than tossed. But what exactly sets these dull-looking host rocks apart from every other piece of roadside rubble? The next clue lies in their appearance under direct light, especially in how they fracture and reflect. That's where visual diagnostics start to separate stone from signal and set the foundation for first-pass screening. A clean, bright gold nugget glinting in a stream is rare and almost never the starting point of a gold-bearing system. The reality is more concealed. Most gold is embedded in matrix rock, and for those hoping to find it, the real work starts by knowing which host materials tend to trap and preserve it underground. Quartz, ironstone, and schist aren't flashy, but they've delivered the majority of the gold mined on Earth. Quartz leads the list, especially in regions shaped by ancient hydrothermal activity. Gold often travels in hot, mineral-rich water forced through fault lines and fractures. When that water cools, it deposits minerals along the way. Quartz forms the bulk of these infill veins due to silica's abundance and low solubility at surface temperatures. Gold comes along for the ride and ends up caught within quartz, sometimes visible, sometimes microscopic. Yet finding a piece of quartz doesn't mean you've found gold. The key is in reading the signs. Is the quartz glassy and clean, or is it milky with iron staining? Clean, vitreous quartz rarely carries much gold. By contrast, quartz with rusty reds, dark veins, or embedded sulfides is more likely to carry hidden value. This includes pyrite, chalcopyrite, and galena, common companions of gold in low to mid-sulfidation epithermal systems. Ironstone is another misunderstood host. Dense and often dark brown or reddish-black, it may carry magnetite, hematite, or goethite. These oxides form where sulfide-rich rocks weather in oxygenated zones, creating what's called a Gaussian cap. While Gaussians themselves may be gold-poor, they sit atop zones where sulfide-bound gold concentrations may lie deeper. If a sample feels unusually heavy for its size and leaves reddish streaks, it's worth investigation. Schist and greenstone, particularly in Precambrian shield regions, represent another major source of invisible gold. Here, intense metamorphic heat and pressure rework original rock layers into foliated textures, often aligning micas, amphiboles, and sulfide streaks. These belts, such as those found in Western Australia, Ontario, and Ghana, can host multi-gram per ton gold in zones too fine to spot by eye. In these cases, panning yields little, but controlled crushing followed by chemical extraction proves otherwise. The myth of visible gold as the primary sign leads many field searchers to ignore their best leads. Instead, recognizing the patterns, rock types, staining, density, associated sulfides is the true route to valuable targets. The visual test is only the start. But to truly read terrain, you have to understand how rivers behave and where gold-bearing rocks tend to settle after erosion starts pulling them down. That behavior plays out most predictably where water slows, and that's the next place to look. Gold rarely travels far. Its density, about 19.3 g/cm3, means it drops out of moving water long before lighter minerals. This same rule applies to gold-bearing rocks. If a vein erodes upstream, fragments of host quartz, ironstone, or schist can ride the current, but only until the water loses speed. That makes one feature more important than any other in placer exploration: the slowdown zone. In rivers and streams, these zones occur at predictable locations. Inside bends are the most consistent trap. As water rounds a curve, centrifugal force pushes faster flow to the outside, while velocity drops sharply on the inner bank. Heavier materials, like gold flakes, nuggets, and especially dense rock fragments, settle into the inside edge. The classic fan of gravels here often hides samples directly descended from upstream gold sources. Another key area is behind obstructions. Boulders, submerged logs, and bedrock rises create eddies where water loses force. In these microenvironments, you'll often find small accumulations of heavy black sands, garnet, magnetite, and mixed in, the denser host rocks that might contain embedded gold. Carefully checking these with a pan or magnet can reveal more than visible gold. They may point to a harder source upstream. Paleochannels, ancient riverbeds now buried or stranded above current water level, also trap gold-bearing stones. These channels often lie parallel to modern streams but are no longer active. Prospectors frequently miss them because they don't show up on topographic maps. But if a terrace holds rounded quartz cobbles and iron-stained gravels well above the river, it may mark a paleochannel. Such zones can hold ancient, preserved gold deposits untouched by modern erosion. In dry washes or arid regions, the same rules apply. Temporary flows from flash floods create a narrow window for gold-bearing material to move. Pay close attention to any visible layering in the sediment. Dense rocks concentrate at the bottom, while lighter sands sit on top. A simple stratigraphic read can isolate test-worthy layers even in completely dry zones. The art here isn't finding gold itself, but recognizing where it likely landed. And when you identify these high-probability zones, your next step isn't the pan, it's reading the rocks that show up there. Some might be nothing. But others, especially dense, rust-stained chunks with embedded quartz or sulfides, are worth more than their appearance suggests. So which rock should make you stop and take a closer look? The answer begins with a sharp contrast, often white, fractured, and stained with rust. It's quartz, but not just any quartz. The kind that speaks of pressure, fluid movement, and metallic residue. A clean white quartz vein cutting through bedrock often goes ignored, mistaken for a common intrusion. But when that quartz is stained, fractured, and runs parallel to a known fault or shear zone, it becomes a prime candidate for gold. Some of the world's richest gold fields, from the Sierra Nevada to the Victorian goldfields, originated in these very veins, where mineral-rich fluids forced open cracks and left behind both silica and metal. The visual giveaway isn't sparkle, it's rust. Iron oxide staining along fractures signals that sulfide minerals once existed there, and in many cases gold rode in with them. Look for orange shred or yellow streaking, especially at fracture intersections or within pocketed zones. In these cases, the quartz often appears gnarly, not glassy but rough, with angular breakage and secondary mineral growth. This is a sign of multiple fluid events, increasing the likelihood of metal deposition. Field testing begins with inspection under sunlight. True quartz is hard, ranking a 7 on the Mohs scale, and will easily scratch glass or show little wear from river tumbling. But you're not just looking for quartz, you're looking for auriferous quartz. This kind may carry flecks of visible gold, which while rare appear as deep yellow streaks or tiny embedded particles, especially along internal fractures. A loupe 10x magnification reveals the difference between gold and pyrite. Gold is malleable, warm yellow, and doesn't reflect in sharp facets. Pyrite, by contrast, reflects with a metallic sheen and cubic edges. In cases where no visible gold appears, weight becomes a clue. A quartz sample that feels heavy for its size may hold sulfide inclusions, iron, lead, or arsenic minerals that often coexist with gold. Tap the rock with a hammer. If it fractures with a gritty texture and exposes dark gray or metallic veins inside, it's worth testing further. Crushed material can be panned or subjected to a streak plate test. Gold leaves a yellow streak, whereas pyrite leaves greenish-black or brown. A promising variant is sugar quartz, where the rock shows granular texture from tiny interlocked crystals. This form often occurs near the top of epithermal systems and can carry fine disseminated gold. Again, iron staining and proximity to altered host rock increase its value as a target. Still, not all quartz is equal. Without context, geological setting, nearby sulfide traces, or structural features, it's just rock. But combine visual traits with known mineral pathways and quartz becomes a powerful signal. The richest veins aren't always exposed. Sometimes they're buried under meters of overburden, betrayed only by scattered float, broken pieces working their way downhill from the load. But not every gold-hosting rock is light or brittle. Some are dense, metallic, and magnetic, born from deeper chemical processes. The next clue hides in darker stone, iron-rich, rust-bleeding, and surprisingly heavy for its size. It's time to turn to ironstone. Many prospectors disregard the darkest rocks in the streambed, the ones that don't shine or fracture like quartz. But in doing so, they overlook one of gold's most frequent companions, ironstone. Heavy, rust-colored, and often magnetic, these rocks are signs of past hydrothermal systems where metal-rich fluids altered the bedrock and left behind an iron-rich shell. And buried beneath that shell, gold often hides in stubborn, sulfur-laced mineralizations. Ironstone forms where iron-bearing minerals oxidize and reprecipitate, especially above sulfide-rich zones. These upper zones, called gossans, develop when pyrite, chalcopyrite, and arsenopyrite are exposed to oxygen and water. The sulfur is stripped away, iron oxidizes, and what remains is a porous, crumbly crust, reddish-brown, yellow, or even dark purple. While the gossan itself may not carry high gold content, it often caps a deeper load that does. The key is not the gold in the gossan, but what it reveals about the chemistry and structure below. Ironstone, in contrast, is denser, more cohesive, and often layered or banded with magnetite or hematite. Magnetite-rich samples will pull a hand magnet slightly, while hematite will not, but both signal oxidized environments conducive to gold deposition. Their surfaces might appear dull, but scratch them, and a metallic red or black streak emerges. Hematite leaves a red streak, magnetite a gray-black. Gold-bearing ironstone may also show quartz stringers or include remnant sulfide blebs visible as brassy grains embedded in the matrix. In hand, ironstone feels heavier than its size suggests. A fist-sized piece can weigh close to a kilogram. If it shows fracture lines with yellowish or brassy specks that don't oxidize over time, those specks might be gold, especially if they smear or flatten under pressure rather than shatter like pyrite. When crushed and panned, ironstone rarely releases visible gold unless it's weathered from a high-grade zone. But roasting the material carefully and legally can drive off residual sulfur and leave behind metallic residues. This must be done with caution. Heating arsenopyrite-bearing samples can release toxic fumes. Only perform roasting in a ventilated, outdoor setting with respiratory protection and away from any structures. Another promising sign is manganese staining, black or deep purple coatings that suggest strong fluid movement. When found alongside ironstone and quartz fragments, it points to zones of intense alteration, often at the edges of mineralized systems. In the field, ironstone is often found as float, broken pieces that eroded from higher ground or vein systems and washed into lower terrain. Follow the gradient upslope and you may find larger, more fractured blocks, sometimes embedded with fine quartz veinlets. If you begin to see an increase in sulfide content or mineral complexity, you're getting warmer. But the most cryptic host rocks aren't stained or magnetic. They're dark, foliated, and often dismissed as background metamorphic material. In the right belts, however, these schists carry microscale gold that resists erosion and can only be unlocked through processing. They don't shine, but they produce. The rocks that look the most unremarkable are sometimes the richest. Schist, with its dull sheen and flaky texture, is often misjudged as worthless bedrock. Yet in the ancient cores of continents, especially within greenstone belts, these metamorphic rocks have quietly delivered millions of ounces of gold. Not in flashy veins, but in fine disseminations and sulfide alignments that only reveal their value through careful testing. Schist is a foliated metamorphic rock, formed under high heat and pressure. It typically contains aligned mica, chlorite, or amphibole minerals, giving it a layered or crinkled appearance. In gold terrains, schist often surrounds or hosts quartz veins, but it can also carry gold within its own structure, especially when altered by hydrothermal fluids. When these fluids penetrate the schist, they can deposit gold along foliation planes within sulfide streaks or in microfractures too fine to see. Greenstone belts, found in regions like the Canadian Shield, Western Australia, and parts of West Africa, are particularly significant. These belts are composed of metamorphosed volcanic and sedimentary rocks, mostly basaltic, and are often laced with shear zones. It's along these shears that gold-bearing fluids move, altering the host rock into carbonate or sericite-rich schists and depositing microscopic gold. The visual clues here are subtle. Unlike quartz or ironstone, gold-bearing schist doesn't draw attention. Instead, fieldworkers look for specific changes: bleaching, softening, or greenish tint from chlorite and epidote alteration. Zones where the rock crumbles under pressure or reveals a silky sheen from a lined mica are suspect. If sulfide minerals like pyrrhotite or arsenopyrite appear along foliation lines, the rock demands further testing. Hardness is moderate, typically around 4 to 5.5, and the rock breaks along its mineral alignment. Schist doesn't react to magnets unless magnetite or pyrrhotite is present, but a magnet test is still useful. A weak pull in the field can indicate the presence of these iron-bearing sulfides. These, in turn, are commonly associated with invisible gold. The main challenge is that gold in schist is rarely visible. Crushing and panning may yield nothing, even from a rich specimen. Instead, fine-grained concentrates must be chemically or thermally treated. A flotation or cyanide assay in a lab might return multiple grams per ton from rock that looked entirely inert. This is why systematic sampling and record-keeping matter. Walk away too soon, and the richest layers stay hidden. If quartz veining or iron oxide staining appears within the schist, that increases the odds. Similarly, finding arsenopyrite or stibnite in the matrix can indicate a low sulfidation epithermal system, exactly the type known to carry invisible gold locked in sulfide lattices. Despite its dull surface, gold-bearing schist often lies directly beneath gold anomalies detected in soil or stream sediments. These rocks don't look valuable, but core samples and lab assays say otherwise. And the more you handle them, the more patterns emerge, certain weights, streak colors, or associated minerals that begin to stand out. But many confuse schist's minor sulfide traces for something more promising. What looks like gold feels like gold but breaks all the rules. That brings us to the most notorious gold imposter in the field, fool's gold and its look-alike cousins. More gold has been wrongly found in the form of pyrite than perhaps any other mineral. Pyrite, often called fool's gold, shares gold's metallic luster and yellowish tint, but it lacks its softness, density, and behavior under test. Worse, pyrite isn't alone. Arsenopyrite, chalcopyrite, and even weathered mica can mimic the look of gold under certain lighting. The key is learning to break the illusion with simple, field-ready logic. Pyrite typically forms in cubic or pyritohedral crystals, with sharp edges and mirror-like reflections. It breaks cleanly along crystal planes and emits sparks when struck with metal. Gold, by contrast, is soft, ductile, and often appears rounded or smeared, especially in rock. One practical test is the pressure smear. Scrape a suspected flake on a hard surface. Gold will leave a yellow streak and deform. Pyrite shatters or scratches without leaving a colored mark. Arsenopyrite complicates things. It forms silvery gray grains with a slight metallic tint and often appears in gold-bearing zones, particularly in metamorphic terrains like schist. A quick crush test and sniff may reveal its true nature. It emits a garlic-like odor due to arsenic compounds. While arsenopyrite itself can carry gold, especially in refractory form, its appearance in a rock doesn't confirm value without further testing. Still, its presence flags potential and justifies deeper analysis. Chalcopyrite, another sulfide, adds to the confusion. It looks brassy, sometimes with rainbow tarnish, and can appear in quartz veins or massive sulfide lenses. It's softer than pyrite but still harder than gold, and its streak is greenish-black. A key tell is its tendency to tarnish to purple, blue, or bronze hues in weathered samples, a visual cue that gold does not share. One of the simplest tests for all these imposters is specific gravity. While gold weighs about 19.3 g/cm3, pyrite comes in at around 5, chalcopyrite at 4.143, and arsenopyrite at 6.1. Even without lab scales, weight in hand reveals the difference. Gold feels unnaturally heavy, especially in small pieces. In quartz, a single gold-bearing inclusion can shift the perceived weight, hinting at unseen value. Microscope or loupe inspection under proper lighting adds clarity. Gold reflects a soft, buttery yellow without facets. Pyrite flashes with mirror brightness and harsh edges. Under magnification, gold shows rounder grains, often tucked into fractures or hosted alongside iron oxides. Imposters tend to stand out unnaturally or appear as part of larger crystalline networks. It's not just about avoiding false positives. These minerals also matter because they often coexist with gold. Arsenopyrite in particular is a common carrier in refractory ores, where the gold is trapped inside its matrix. Such ores require roasting or pressure oxidation to release the metal, a process not suitable for field extraction, but highly relevant to long-term value and lab submission. So the smarter question isn't just is it gold, but does this carry gold? And once you've ruled out the fakes and flagged promising hosts, the real work begins, isolating samples, testing by pan, and logging where the best ones came from. That starts with a field method that requires no chemicals, no heat, just gravity, water, and a few simple tools. It's time for the first real pass. Before lab assays, chemical tests, or metallurgical analysis, there's a simple centuries-old way to screen a rock for gold: crush and pan. This first pass isn't about proving grade, it's about identifying which samples justify deeper work. And with nothing more than a hammer, a steel mortar, and a gold pan, you can test a rock's potential in under an hour, right in the field. Start with your suspect rock, ideally quartz, ironstone, or schist showing iron staining, sulfide specks, or dense mineralization. Using a steel mortar and pestle or even a heavy-duty cloth bag with a rock hammer, crush the sample to sand-sized particles. You're aiming for 1 granules. If the sample resists breaking or shatters with glittery chips, note it. Quartz tends to crush cleanly, while sulfide-rich rock may crumble into a fine, greasy powder. Transfer the crushed material into a gold pan. Add water and begin the standard panning sequence: agitation to stratify heavies, tilting to wash away light fractions, and tapping to concentrate the dense particles in the bottom riffle. As you progress, keep watch for 3 key indicators. First, color. Visible gold appears as deep yellow, dense, and non-reflective under direct sunlight. Unlike mica or pyrite, it won't flutter or float, and it remains pinned even in fast-moving water in the pan. Micron-sized particles may show up as a faint yellow dust or flash layer. This requires experience to distinguish from background light. Second, behavior. True gold doesn't bounce or dance. It stays low, slides heavily, and resists movement. If it smears when rubbed with a finger against the pan bottom, it's likely gold. Pyrite, by contrast, is brittle and breaks. Third, heavy sweet. Even if no gold appears, note the presence of black sands, garnet, and lead shot, if in active shooting areas. Their presence indicates proper stratification and suggests your pan captured everything the rock had to give. If visible gold appears, even in trace, log the sample's location, depth, and orientation. Use a GPS or field map grid, mark the sample number, and consider taking bulk material for follow-up testing. If the sample pans clean but came from an area with known mineralization, don't discard it yet. Some gold is too fine to see and still economically viable with processing. Keep in mind that crushing in the field may not release all gold. Coarse particles locked in quartz or sulfides often require finer milling, sometimes down to 100 mesh/150 microns to fully liberate metal. But for a first-pass screen, this method delivers a practical pass-fail signal. Does this rock contain testable free gold? Sometimes you'll get a faint flash, sometimes nothing. But occasionally a rock releases a fine gold trail that confirms it came from a productive system. Before getting too excited though, a second layer of testing, one that weeds out iron and pinpoints magnetic fractions, can sharpen the signal. That's where magnetics and streak testing take over. A promising pan test is only half the story. Gold may be present, but in what form, and how much of the rock's mass was just iron or sulfide waste? To refine your understanding, the second pass adds 2 quick, low-cost tools: a strong neodymium magnet and a ceramic streak plate. Together, they separate deceptive heavies from true indicators, flagging samples that might mislead early enthusiasm. Start with the magnet. Sweep it slowly over your dry concentrate or crushed rock tailings. If large amounts of material leap to the magnet, you're dealing with magnetite or highly magnetic pyrrhotite. Both are dense and common in altered zones, but gold itself is non-magnetic. This means high magnetism doesn't confirm gold, but low magnetism in a heavy sample can raise its probability. Take note of resistance too. Ilmenite, often confused with black sand, is weakly magnetic and may slide or shift under the magnet rather than jump. Mark these responses carefully. The magnetic profile helps distinguish host rock types. Next, apply the streak test. Rub a small, sharp corner of your mineral or heavy inclusion across an unglazed ceramic tile. Gold leaves a rich yellow streak, soft, powdery, and instantly visible. Pyrite typically yields a dark green-black or brown streak. Hematite shows red, magnetite gray-black. Chalcopyrite, often mistaken for gold in quartz, leaves a greenish-black mark. These subtle differences break the illusion where appearance alone fails. When tested together, the results clarify rock character. A sample that's heavy, non-magnetic, and leaves a yellow streak is worth serious attention. One that's magnetic and brown-streaked may still host gold in association, especially if sulfides are present, but it requires further steps like roasting or chemical digestion. Conversely, a sample that's magnetic with a gray-black streak and no visible gold is likely iron oxide or a magnetite-rich gangue, valuable only as a geological clue, not a product. These tests also help isolate gold-bearing sulfides from barren ones. Arsenopyrite may appear non-magnetic and produce a dark gray streak. While not gold itself, it often contains submicroscopic gold locked in the crystal lattice, refractory but real. If found in altered schist, near quartz veins, or in zones with iron-stained float, it's a strong indicator of a productive system. Use your observations to categorize each sample. Direct gold visible in pan, yellow streak, low magnetism. Associated sulfides, non-visible gold, moderate magnetism, dark streaks, and background rock, magnetic, non-reactive, no streak. Keep samples from the first two categories and discard or archive the third, unless it shows textural clues worth tracking. As the signal refines, it's common to discover gold isn't free, it's locked inside sulfide grains or resistant quartz. To test these further, a more aggressive technique is required. By applying controlled heat, you can oxidize away the bindings and reveal any hidden gold, but that comes with risk, regulation, and safety demands. The next step, roasting, is both revealing and cautionary. At this stage, if panning shows no gold but magnetic and streak tests point to sulfide-rich material, the next option is roasting. Roasting drives off volatile elements, mainly sulfur, and oxidizes metal sulfides like pyrite, arsenopyrite, or chalcopyrite. When done correctly, this process frees fine gold locked inside sulfide matrices and can turn a dead-looking rock into a visibly gold-bearing residue. But it's not a casual step. It demands control, knowledge, and respect for health and environmental risks. Begin by drying and finely crushing your rock sample to at least 100 mesh, or about 150 microns. The finer the material, the more surface area is exposed, which increases the reaction efficiency during roasting. Spread the powdered sample in a thin, even layer on a metal tray, preferably stainless steel or ceramic, and place it in a heat-safe, well-ventilated outdoor area. This is non-negotiable. Roasting can release toxic fumes, particularly if arsenopyrite or stibnite is present. Use a propane torch, furnace, or kiln to raise the sample's temperature gradually. Aim for 500-700 degrees C, 932-1292 degrees F. At these temperatures, pyrite Fe(S2) oxidizes to iron oxide Fe2O3 and sulfur dioxide SO2, while arsenopyrite Fe(S) breaks down into iron oxide, arsenic trioxide as 2O3 and sulfur gases. These emissions are hazardous. Wear a full-face respirator rated for chemical fumes and work with wind direction and plenty of open space. As roasting proceeds, watch for color changes. The sample will darken, then lighten as sulfides convert to oxides. Pyrite turns from brassy yellow to red-brown, arsenopyrite chars to black, then oxidizes to a reddish or pale residue. This transformation can take 30 to 90 minutes depending on mass and composition. Allow the sample to cool completely before handling. Once cool, inspect visually. In some cases, fine gold particles become visible, dull yellow dust or tiny specks in a matrix of oxidized minerals. You can now perform another pan test or sluice the residue. This time, if gold was previously bound in sulfide minerals, it should appear more freely. If no visible gold emerges, the process still isn't wasted. Roasting deactivates sulfur compounds that would otherwise interfere with chemical leaching methods like cyanidation or thiourea. It also tells you something important, whether gold is physically present but trapped, or whether it never existed in the sample to begin with. For field scenarios, a successful roast that yields visible gold confirms that the rock carries refractory ore, material where gold is real but locked. This class of ore often goes unrecognized and dismissed because early tests come back empty. But it can be commercially viable, particularly when found in volumes or near established gold systems. Still, not every test yields clarity. Some materials resist all visual detection and give no gold even after roasting. Others hint at deeper potential but require more than the eye can deliver. For those, many turn to UV fluorescence or advanced scanning tools. But when it comes to gold, UV rarely helps, and understanding why it fails can save both time and false hope. Ultraviolet light can expose hidden patterns in minerals invisible under normal lighting, but not in gold. Unlike many other elements, native gold does not fluoresce under long-wave or short-wave UV. That means scanning a rock with a UV torch will not cause gold itself to glow, regardless of purity or size. Yet UV still has a role indirectly. It reveals associated gangue minerals, alteration zones, and structure hints that can imply, but not confirm, the presence of gold. One of the most common false expectations is that glowing equals value. In gold systems, this logic fails. A vein of calcite might glow brilliant pink under UV, yet carry no economic mineralization. Conversely, a dull, dead-looking chunk of schist or sulfide quartz that shows zero fluorescence might hide several grams per ton in refractory gold. The danger isn't in using UV. it's entrusting it as a filter for gold potential. That said, UV light can flag certain minerals commonly found with gold. Scheelite, a tungsten ore, glows bright blue under shortwave UV and often accompanies gold in skarn or hydrothermal deposits. Fluorite, which fluoresces violet or blue, may appear in veins that also carry auriferous quartz, though its presence alone isn't diagnostic. Similarly, willemite, calcite, and even feldspars can show varied fluorescence in altered systems. They don't guarantee gold, but they map zones where mineral-rich fluids once flowed. UV light can also expose structural features. Tiny veins, zoning boundaries, or overgrowths invisible to the eye sometimes fluoresce differently, revealing cross-cutting relationships between host rock and later mineralizing events. In certain cases, this helps trace the path of hydrothermal fluids that may have carried gold, even if the gold is invisible or unreleased. In sulfide-rich rocks, a lack of fluorescence is typical. Pyrite, arsenopyrite, chalcopyrite, and other common gold associates are inert under UV. Their mass and density may dominate the rock's chemistry, but they offer no optical cues. That means in gold-focused work, UV is a secondary or contextual tool, not a filter, not a validator. There are exceptions worth noting. Some gold-containing minerals, like electrum, a gold-silver al, can occasionally reflect weakly under certain wavelengths, but this is not true fluorescence and requires specialized equipment, not handheld UV lamps. Other elements, like uranium or rare earth oxides, can glow brightly and distract from the real targets. Bottom line, if a rock glows, it's not gold. If a rock doesn't glow, it still might be. Use UV to learn the story of mineral movement and structure, not as a proxy for value. So how then do you increase confidence that a sample, especially one without visible gold, is worth further pursuit? You turn to its elemental neighbors. Gold doesn't travel alone, and its indicator suite tells the deeper story. Those subtle mineral companions often appear first and guide the way. Gold may be the prize, but it rarely travels solo. In hydrothermal systems, it's escorted by a distinct suite of elements and minerals, clues that precede or surround the gold itself. Understanding this indicator suite means learning to read the trail gold leaves behind, even when it's locked or invisible. These companions don't just hint at gold, they help define its genesis, depth, and extraction path. The primary indicators include bismuth, tellurium, antimony, arsenic, and tungsten, each linked to specific types of gold systems. Their presence in a rock doesn't confirm gold, but it greatly increases the odds, especially when found together in zones of structural disturbance, quartz veining, or sulfide alteration. Start with arsenic, most often hosted in arsenopyrite. This silvery white sulfide with a metallic sheen frequently accompanies gold in metamorphic belts, greenstone terrains, and shear zones. Even when gold doesn't appear, arsenopyrite is a red flag. It often forms under the same temperature-pressure conditions as gold-bearing fluids and can trap microscopic gold within its crystal lattice, refractory but real. Bismuth minerals like bismuthinite and native bismuth show up in intrusive related gold systems and are particularly diagnostic of high-temperature settings. Their presence often correlates with visible gold, especially in massive quartz veins or skarn environments. Bismuthinite has a metallic gray luster and forms in slender, blade-like crystals, fragile but revealing. Tellurium shows up in minerals like calaverite, gold telluride, sylvanite, and petsite. These are among the few minerals where gold is chemically bonded within the structure, not just physically mixed. Telluride ores often yield high gold grades but are easy to misclassify in the field. They appear brassy, sometimes with a subtle metallic rainbow, and must be confirmed via test or lab assay. The Cripple Creek and Calgary gold districts are famous for telluride-rich gold. Tungsten, usually found as scheelite, is another valuable proxy. In UV tests, scheelite fluoresces bright blue-white under shortwave light and often occurs in skarns or contact metamorphic zones where gold also concentrates. Its hardness and density can mimic quartz, but under UV it reveals itself instantly, making it one of the few fluorescence-based hints worth noting in gold exploration. Antimony, especially in the form of stibnite Sb2S3, is a jet-black metallic mineral with a striking elongated crystal habit. It appears in low-sulfidation epithermal systems and often flags gold-silver potential. Though brittle and toxic in dust form, its occurrence in veined or brecciated zones marks strong mineral fluid movement and thermal overprinting, exactly the conditions that also favor gold deposition. Field identification of these indicators relies on a combination of visual traits, context, and weight in hand. Most are denser than the surrounding host rock. Some are weakly conductive or magnetic. But taken together, they create a pattern. A rock with arsenopyrite streaks, shale-like glow, and quartz veining in a structurally deformed zone is vastly more likely to carry gold, even if none is immediately visible. The key is correlation. No single indicator is sufficient, but when multiple appear in sequence, especially across a few square meters, they sketch the outline of a mineralized system. That's where gold thrives. And yet many dismiss these signals too early, particularly when quartz appears ordinary. In fact, the most valuable quartz can look deceptively bland, until you know how to listen to what it's hiding. Quartz is everywhere, on trails, in rivers, beside road cuts, and most of it holds no economic value. That abundance leads many to overlook what might be the most important mistake in gold exploration: misjudging auriferous quartz as ordinary filler. The richest quartz often shows no visible gold, no special luster, and no dramatic color. It looks like any other stone. But inside, it may carry fine gold worth thousands per ton. The problem starts with expectation. People assume valuable quartz should glitter, glow, or look unusual. In truth, the quartz that carries gold often appears milk-white, fractured, or iron-stained, traits shared by thousands of barren rocks. The difference isn't obvious, but it's there, hiding in texture, density, and context. And when those signs are missed, prospectors walk away from high-grade zones without knowing it. One of the strongest yet subtle signs is rusty fracturing, a pattern of thin, jagged cracks filled with iron oxide. This occurs when sulfides once present in the quartz oxidize, leaving behind hematite, limonite, or goethite. These oxides stain the fracture planes in red, yellow, or brown and suggest past fluid movement. In gold-bearing systems, these same cracks were the transport paths for silica and gold. Another misjudged feature is bleached or sugary texture. Some quartz appears granular, like compressed sugar. This sugar quartz forms at low to moderate temperatures near the top of epithermal systems and often carries fine disseminated gold. It lacks the glassy luster of pure silica and may feel brittle or chalky under the hammer. Its softness doesn't mean it's worthless. In many cases, it's more productive than its harder, cleaner cousins. Weight is also deceptive. A piece of auriferous quartz may feel unusually dense for its size, not due to gold alone, but from embedded sulfides like pyrite or arsenopyrite. These don't always show on the surface. Only by crushing and concentrating can their presence be confirmed. When panned, even a single heavy inclusion in the crushed material might leave behind fine gold specks that change the valuation of the entire outcrop. Location is everything. Quartz found along shear zones, fault intersections, or near Gaussian caps deserve special attention. In greenstone belts and ancient volcanic terrains, these structures act like gold highways. A quartz vein crossing one of these faults might look dull, but geologically it's in the perfect position to host mineralized fluids. Ignore it and you miss the source. The mistake becomes most costly when float samples, loose chunks of quartz on the ground, are dismissed. These pieces may have broken off from buried veins or been carried downslope from rich deposits. Without testing, they vanish into the tailings pile. With testing, they sometimes rewrite the entire map. The lesson is simple but overlooked. Gold doesn't change the look of quartz unless it's in visible flakes or veins, and that's rare. Most of the world's productive gold quartz is indistinguishable from background rock until broken, crushed, and tested. And when you reach that point, when you have multiple samples that passed visual, pan, magnet, streak, and roast tests, it's tempting to go all in. But before spending heavily on lab assays or extraction, one more question remains. Can modern field tools give a reliable read? That's where portable tech makes its entrance. Some tools can help. Others deceive. Modern prospectors increasingly turn to technology for answers in the field, but not all tools deliver what they promise. Handheld X-ray fluorescence (XRF), analyzers, and portable assay kits offer fast readings, but they have limits. Understanding where they shine and where they fail is critical to avoid costly misreads and overconfidence, especially with gold-bearing rock. The XRF analyzer is the most commonly marketed high-tech field tool. It uses focused X-rays to excite atoms in a sample and measures the secondary fluorescence emitted. From this, it calculates elemental composition: iron, lead, arsenic, copper, and more. But here's the catch: gold often flies under its radar. Native gold's fluorescence is weak and easily masked by heavy elements like lead or bismuth. Unless present in high concentrations near the surface, gold rarely registers reliably on handheld XRFs. What XRF does well is identify gold's companions. High levels of arsenic, bismuth, antimony, or tellurium, especially in conjunction with elevated iron or sulfur, strongly suggest hydrothermal mineralization. In quartz veins or altered schist, XRF can quickly confirm the presence of indicator elements, giving rapid insight into which samples merit deeper testing. It's especially useful when tracking changes across a grid or trench, spotting geochemical halos that surround gold deposits. For more direct testing, portable assay kits enter the picture. Some kits use acid digestion followed by colorimetric strips or chemical precipitation to identify gold in crushed samples. Others involve cyanide or thiourea leach solutions that dissolve free gold over hours or days. These methods can confirm presence, but are sensitive to contamination, sample prep, and reagent accuracy. DIY fire assays, though theoretically possible, are dangerous and legally restricted in most jurisdictions due to the use of lead, high temperatures, and toxic byproducts. Unless performed in a lab setting with proper gear, they risk more than just bad data. However, simple bottle leach tests or gravity-based methods, such as sluice mats or shaking tables, can provide semi-quantitative reads if you're working with visible gold or rich concentrates. One overlooked tech is the digital scale. When dealing with panned concentrates, the ability to weigh sub-gram yields from crushed samples adds objectivity. A test sample yielding even 0.05 grams of gold from 5 kg of rock suggests a grade of 10 grams per ton, a potentially profitable return depending on recovery costs. Combining pan yield, sample weight, and location data builds a stronger field case than instruments alone. Still, no field tool replaces the final step, certified lab assay. What XRF and portable kits provide is screening. They flag where to focus, narrow down promising zones, and avoid wasting lab fees on barren samples. But when a rock passes all tests, carries indicator signals, and yields a visible return under basic processing, the next question is location, because not all terrains are equally promising. So where does this workflow apply best? The answer lies in understanding regional geology. Certain belts, formations, and fault zones produce these clues consistently. Others mimic them but lead nowhere. Filtering by region can save years of wasted effort. Not all ground is created equal. Some regions routinely deliver gold-bearing rocks with consistent indicator suites, while others offer lookalikes with no economic yield. Knowing where your workflow aligns with geology, greenstone belts, subduction zones, hydrothermal arcs, can turn scattered clues into a reliable exploration path. From the ultramafic cratons of Western Australia to the faulted metamorphics of the Yukon, geography defines potential. In Western Australia, particularly the Archean Yilgarn Craton greenstone belts are king. These belts, composed of metamorphosed basalt, ultramafic flows, and interbedded sediments, host quartz veins rich in gold, frequently accompanied by arsenopyrite, stibnite, and magnetite. Here, gold is found in shear-hosted quartz veins cutting schist, often with visible iron oxide staining. Pan gold is rare. The value lies in crushing and assaying fine-grained rock. Indicator elements like bismuth and tellurium frequently show up on XRF scans, adding confidence. In British Columbia and the Yukon, gold follows different rules. Epithermal systems dominate, quartz stockworks within volcanic or sedimentary basins, especially near known faults. These zones produce oxidized gossans, iron-rich caps, and float material with scattered visible sulfides. Rocks here may fluoresce if scheelite is present, and stream sediment sampling remains one of the most effective strategies. Visible gold can occur in quartz, but more often it's fine and locked within arsenopyrite. The U.S. Rocky Mountains, especially Colorado and Nevada, host intrusive-related and Carlin-type systems. Here, gold often appears in carbonate rocks, disseminated across large areas with no visible mineralization. However, arsenic, antimony, and thallium dominate the Pathfinder suite. In these cases, XRF becomes invaluable, not for seeing gold, but for detecting the chemical halo that surrounds it. The rock may look like ordinary limestone or dolomite until crushed and leached. In South Africa, the Witwatersrand Basin provides a completely different model, gold locked in conglomerates. These rocks appear as ordinary pebbly sandstone, but carry invisible gold particles trapped in ancient river gravels. Processing here requires bulk sampling and chemical extraction. Field testing is nearly impossible without lab-grade methods. Alaska mirrors aspects of British Columbia and Russia's Far East, gold and quartz veins, sulfide-rich schists, and placer concentrates sourced from decaying lodes. Auriferous quartz here often runs milky white with orange iron staining, sometimes showing visible flakes. Streambeds produce coarse gold and host rocks with black sand, garnet, and occasional tellurides. Classic panning is effective, but roasting and detailed mapping distinguish real sources from false float. Across these regions, consistent patterns emerge. In greenstone belts, look for foliated schist, quartz veining, and arsenic bismuth suites. In epithermal terrains, gossan, stibnite, and fluorite signal past fluid movement. In carbonate replacement zones, gold may be invisible but traceable through chemical halo. In placer-rich areas, upstream float tracking is essential to locate the parent source. Field success isn't about luck, it's about geological fit. If your methods align with the local system, even bland-looking rock can yield high returns. If not, the best tools won't help. But even in the right place, timing and access matter. Before taking a sample home or lighting a torch, you must account for the practical boundaries, permits, fire risk, and safety in often unstable ground. Without that, discovery becomes danger. The path to discovery is lined not just with rocks, but regulations, and the risks of ignoring them go far beyond fines. Gold-bearing terrain often overlaps with fire-prone zones, unstable slopes, and land under legal restriction. Whether you're sampling quartz veins, roasting sulfides, or trenching into gossan caps, safety and legality are as critical as test results. Overlook either, and you risk forfeiting claims, damaging ecosystems, or facing criminal penalties. Access rights come first. In most regions, collecting mineral samples, even on public land, requires either a prospecting license or landowner permission. This includes Forest Service lands, Crown Land, and Bureau of Land Management (BLM) tracts. Failure to check land status can invalidate any future claim or investment. Before taking even a fist-sized sample, verify the location's mineral rights status using national or state-level GIS platforms. Mark GPS coordinates and maintain a sampling log with names, dates, and collection notes. Claim staking is the next step if a productive zone is confirmed. Each jurisdiction has its own process, but common rules apply. Location boundaries must be marked, samples logged, and discovery work recorded within specific timelines. Some areas like British Columbia offer online staking. Others require physical markers and filings with local mining offices. If you're near existing claims, respect their boundaries. Trespassing can result in legal action or loss of access to key zones. Roasting ore, even in small quantities, requires special care. Sulfide-bearing rocks, especially those containing arsenopyrite or stibnite, release hazardous fumes when heated. Roasting in fire-restricted areas or without proper fume management risks wildfires and toxic exposure. Always perform this process on non-flammable ground, in ventilated zones away from vegetation or structures. Use containment trays and have suppression gear, extinguisher, water, sand on hand. In dry climates or during fire bans, avoid roasting altogether. Slope stability is another hidden threat. Many gold-bearing zones occur in altered, fractured rock near fault zones. These areas may seem solid but crumble when undermined or saturated. Digging or sampling near vertical cuts or overhangs, especially in riverbanks or old workings, demands caution. Test footing, work in pairs, and avoid undercutting boulders or trenching in rain-soaked ground. Remote areas also present risks of wildlife encounters, exposure, and navigation errors. Always carry communication tools and leave a trip plan. Chemical testing, while less common in field scenarios, also introduces risk. Acid-based kits can cause burns or toxic reactions if mishandled. Store reagents in sealed, labeled containers, wear gloves and eye protection, and neutralize spills immediately. Never mix acids in unventilated areas or near sulfide materials. Lastly, ethical collection matters. Don't strip out quartz veins, destroy exposed outcrops, or leave trash in sensitive environments. High-impact methods like blasting, mechanized digging, or bulk sampling without permits violate both legal and conservation rules. Responsible prospecting protects your reputation and preserves access for future exploration. In short, the best find is the one you can legally and safely keep. And once those conditions are met, once you've got gold-positive rock, permission to work it, and a secure claim, the next move isn't further testing. It's designing a plan to verify the extent of the deposit. That means grid work, repeat sampling, and identifying where to invest in full assays. Only then can the rock's real value be confirmed. A single promising rock is just that, an isolated event. To convert a sample into a discovery, you need a system, a repeatable, location-bound verification plan that separates lucky finds from geological reality. This is where grid sampling, data tracking, and strategic assays come into play. Without them, the path from indication to valuation breaks down. Start with a grid. Once a rock tests positive, whether through visible gold, favorable indicators, or pan concentrates, mark its location precisely with GPS or a physical flag. Then lay out a systematic sampling pattern across the area, typically in 5x5 or 10x10 meter squares, depending on terrain and access. The goal is to define the lateral continuity of the host structure, whether it's a quartz vein, shear zone, gossan, or contact boundary. Within each grid square, take a representative rock sample, ideally from outcrop or float with consistent textural traits. Record the exact coordinates, elevation, sample weight, and visual features, color, staining, associated minerals, density, feel. If possible, crush and pan each sample on site. Look for trends. Are visible sulfides increasing? Does iron staining become more intense? Are gold flecks or heavies showing up repeatedly? Repeatability is key. A single positive pan could be noise, but if multiple grid points show gold across a zone, especially when magnetics and streak tests match, it indicates a coherent system. Document any directional trends. If gold-bearing quartz aligns NWSE, extend the grid accordingly. Conversely, if indicators fade beyond a certain point, you've found a boundary worth noting. Once a few hot spots emerge, scale up sample volume for selective lab assays. Start with fire assay if visible gold is present, or cyanide leach for fine or refractory ore. For rocks with high sulfide content, consider submitting pulped material for multi-element ICP-MS or XRF scans to confirm the Pathfinder suite. Prioritize samples that show gold presence and favorable geochemistry, arsenic, bismuth, tellurium, tungsten, to cross-validate the system's character. Budget wisely. Not all samples need immediate lab work. Use field tools to triage. If a crushed sample yields nothing in pan or magnet test, skip it for now. Focus funds on confirming the richest signals and defining the footprint of mineralization. Don't neglect depth. Surface samples may not represent grade at mineable levels. If outcrop allows, chip into walls or sample vertical faces across weathered and fresh zones. Gold content can increase below oxidation layers, especially in sulfide systems where the upper material has been leached. Finally, log every action. Keep a field notebook or digital spreadsheet with sample IDs, GPS points, test results, and photos. This record will form the basis for reporting to labs, staking a formal claim, or securing funding. Without it, even strong results lack credibility. Once multiple positive assays confirm grade continuity, the question shifts again from is there gold to what is it worth? Now it's time to face market reality, not just what's in the rock, but what it's likely to sell for. That depends on grade, volume, and what kind of gold you're actually holding.